Acceleration due to gravity. Acceleration due to gravity. The acceleration created by gravitational force of attraction is called acceleration due to gravity. The acceleration created by gravitational force of attraction is known as acceleration due to gravity. We know that a force exists between Earth and a body placed at some distance from the center of the Earth. Suppose a body of mass small m is just above the surface of the Earth and its distance from the center of the Earth is say small d and mass of Earth is capital M. Then the force of attraction between small m and capital M is given by F is equal to G capital M small m divided by d square. This is the force of attraction. This force of attraction acts on both the bodies, on small m as well as on capital M. So, because of this force, the acceleration created to small m is given by A is equal to F by small m. A is equal to F by small m. From this relation, we will get acceleration. This acceleration is acceleration due to gravity, which is 9.8 meters per second square. Now, what about the acceleration on Earth due to this force? Acceleration on Earth. To find the acceleration on Earth, we have to consider the same force F is equal to G capital M small m by d square. This is the force that acts on Earth. Of course, it acts towards the mass small m. This force creates acceleration on Earth. The acceleration created on Earth is A is equal to F by m, capital M. F divided by capital M. To understand the value of this acceleration, let us take the relation F by m. This F is nothing but mg, small mg, where small m is mass of the body just above the surface of the Earth. G is acceleration due to gravity. The value of G is 9.8 meters per second square. Let us take the small m mass is an apple whose mass is about 0.2 kgs, 200 grams. And the mass of the Earth is capital M is equal to 5.98 into 10 to the power of 24 kgs. The mass of the Earth is 5.98 into 10 to the power of 24 kgs. Using these values, if you calculate the acceleration on Earth, this acceleration will be almost negligible compared to the value 9.8 meters per second square. Though the same force acts on a body of mass small m and on Earth, the acceleration on body of small m is 9.8 meters per second square, whereas the acceleration on Earth is negligible. How acceleration due to gravity is viewed, observed? The value of acceleration due to gravity is the same on all bodies irrespective of their mass. Irrespective of the mass, the same acceleration acts on all the bodies. This acceleration is always directed towards the center of the Earth. The direction of this acceleration is towards the center of the Earth. Generally, when bodies are moving downward direction will be considered as positive. Hence, acceleration due to gravity will be taken as positive. So, if we consider downward direction as positive, then acceleration due to gravity will be positive. But when the bodies are moving up, upward direction will be considered positive. In such a case, acceleration due to gravity becomes negative. So, if upward direction is positive, G is negative. If downward direction is positive, G is positive. Normally, its value will be taken as 9.8 meters per second square. Though this value varies from place to place, in general, while working out problems, we take the value of G as 9.8 meters per second square. We apply the modified equations in the case of a freely falling body. A freely falling body means its initial velocity u is equal to 0. So, the kinematic equations, they will be modified, they get reduced to the form v is equal to gt S is equal to half gt square, v square is equal to 2gh, Sn is equal to g into n minus half. The relations in kinematics, they will be reduced to the form v is equal to zt, S is equal to half gt square, v square is equal to 2gh, Sn is equal to g into n minus half for a freely falling body. What is the velocity after 1 second, 2 seconds, 3 seconds, etc.? Now let us pass on to calculate these velocities. Velocity acquired by a freely falling body. This can be calculated from the relation v is equal to gt. G is 9.8 meters per second square. So after 1 second, t is 1 second, so it becomes 9.8 into 1, 9.8 meters per second. After 2 seconds, 9.8 into 2, 19.6 meters per second. After 3 seconds, 9.8 into 3, 29.4 meters per second. Like this, we can calculate the velocity after 1, 2, 3 seconds, etc. Now let us proceed to calculate the displacement of a freely falling body in 1, 2, 3 seconds, etc. We take the relation S is equal to half gt square. In this equation, if we put g is equal to 9.8 and t as 1, we will get the displacement in the first second. That is half into 9.8 into 1 square is 4.9 meters. The displacement in 2 seconds is given by half into 9.8 into 2 square, which is equal to 19.6 meters. The displacement in 3 seconds is half into 9.8 into 3 square, that is 44.1 meters. Like this, we can calculate the displacements in 1, 2, 3 seconds, etc. Let us try to find the ratio of these displacements. The ratio will be 4.9 is to 19.6 is to 44.1 is to 78.4 is to dash dash dash. We notice that 4.9 gets cancelled in all these values. Hence, we will get the ratios as 1 is to 4 is to 9 is to 16. This is the ratio of the displacements of a freely falling body. 1 is to 4 is to 9 is to 16 is to dash dash dash. Now let us calculate the displacements in first, second, third seconds, etc. For this, let us take the relation Sn is equal to g into n minus half. Sn is equal to g into n minus half. When we take n as 1, we will get S1. S1 is equal to 9.8 into 1 minus half, which will be equal to 4.9 meters. S2, that is the displacement in the second, that is 9.8 into 2 minus half, that is 14.7 meters. S3 is the displacement in the third second, that is 9.8 into 3 minus half, 24.5. See in the figure the displacements given in first, second, third seconds. In the first second is 4.9. From there, the displacement will take place in the second, which is 14.7. From 14.7 onwards, the displacement is 24.5 meters. That is the displacement in the third second. Like this, we have to imagine the displacements in first, second, third seconds, etc. The ratio of these displacements S1 is to S2 is to S3 is equal to 1 is to 3 is to 5 is to 7 is to dash dash dash. 4.9 is to 14.7 is to 24.5 is to dash dash dash. This reduces to the form 1 is to 3 is to 5 is to 7. Velocity acquired after descending a height h. To calculate this velocity, we use the relation v is equal to square root of 2gh. V is equal to square root of 2gh. Suppose if you want to calculate the velocity after descending 4.9 meters, then we can calculate the velocity as square root of 2 into 9.8 into 4.9, which is equal to 9.8 meters per second. That means a freely falling body acquires 9.8 meters per second velocity after descending 4.9 meters. Suppose it descends 19.6 meters, then the velocity will be 19.6 meters per second, which is obtained by calculating square root of 2 into 9.8 into 19.6. Similarly, if it descends 78.4 meters, then its velocity will be 39.2 meters per second. This can be calculated from the relation square root of 2 into 9.8 into 78.4, which is equal to 39.2 meters per second. Like this, we can calculate the velocity acquired by a freely falling body after descending certain height h. Equations of motion of vertically projected bodies. Equations of motion in the case of vertically projected body. Let us take the basic relations v is equal to u plus at, s is equal to ut plus half at square, v square minus u square is equal to 2as, sn is equal to u plus a into n minus half, etc. And then use, suppose the initial velocity with which a body is projected is u. Then upward direction is considered positive. So acceleration due to gravity is to be taken as negative. So g is to be taken as minus g. Then substituting g as minus g, we will get v is equal to u minus gt, s is equal to ut minus half gt square, v square is equal to u square minus 2gh, sn is equal to u minus g into n minus half. These are the relations that will be applied to the bodies projected vertically upward. Velocity of vertically projected body. Let us consider a body projected with a velocity 39.2 meters per second. Let us consider a body projected upwards vertically with a velocity 39.2 meters per second. We use the relation v is equal to u minus gt. After 1 second, the velocity becomes v is equal to 39.2 minus 9.8 into 1, which is equal to 29.4 meters per second. So after traveling for 1 second, its velocity will be reduced to 29.4 meters per second. Then after 2 seconds, v is equal to 39.2 minus 9.8 into 2, which is equal to 19.6 meters per second. So after 2 seconds, the velocity becomes 19.6 meters per second. After 3 seconds, it becomes 9.8 meters per second. After 4 seconds, it becomes 0. Like this, we calculate the velocity of a projected body after 1, 2, 3, 4 seconds, etc. Displacement of vertically projected body. Suppose the body is projected with 39.2 meters per second, then its displacement, vertical displacement, can be calculated with the relation s is equal to ut minus half gt square. We calculate displacements with the relation s is equal to ut minus half gt square. After 1 second, it becomes 34.3 meters. In 2 seconds, it becomes 58.8 meters. In 3 seconds, it becomes 73.5 meters, and in 4 seconds, it becomes 78.4 meters. We calculate these values from the relation s is equal to ut minus half gt square, where u is equal to 39.2, g is 9.8. Displacements in 1, 2, 3, 4 seconds, etc. of a vertically projected body. If you take the same body which is projected with a velocity 39.2 meters per second, then displacement in 1, 2, 3, 4 seconds, etc. will be calculated with the relation Sn is equal to u minus g into n minus half, u minus g into n minus half, where u is equal to 39.2, g is 9.8 meters per second square. Using these values, if we calculate, we will get S1 is equal to 34.3 meters, S2 is equal to 24.5 meters, S3 is equal to 14.7 meters, and S4 is equal to 4.9 meters. These values are shown here at the right side.